Hi, Math 30-2s. Today we're going to start into the second day of combinations. What you're going to see today, okay, as opposed to yesterday, are some key phrases, okay? So at least, at most, okay, things along those lines. And you're also going to see something that we deal with today called the complement, which allows us to solve a question in a much simpler way than a big long calculation. And obviously I'll highlight that and make those questions known to you as we approach them in today's lesson. So just jumping into questions, the first one reads like this. The student council decides to form a subcommittee of 5 council members to look at how funds raised should be spent on the students of the school. There are a total of 11 student council members, 5 males and 6 females. How many different ways can the 5-member subcommittee be chosen if there are? And then we have 3 scenarios here. Now, again, if I came across this type of question on a test or a quiz, the first thing I would notice is that on this committee, there is no president, no vice president, no secretary, those types of things, no roles assigned to positions. Therefore, I know it's not a permutation, it's just a combination, okay? I just want to choose the committee, and the people need to be on the committee or not on the committee. So this is automatically a question that deals with combinations. So in A, okay, there's no restrictions on the number of females or males. So another way of wording that is just how many ways can you choose that committee? Well, there are 11 people to select from, 5 males, 6 females, and I need to choose 5, right? They are choosing a 5 council committee, okay, out of a total of 11 students. So just 11 choose 5. So again, on our calculators, okay, access through math, probability, okay, option 3, which is the combinations, and 462, okay, is the total number of ways that that committee can be chosen without any restrictions. Now in B, okay, we start to see these key words. Now we saw this one yesterday, exactly 3 females. So that means 3 females, no more, no less. And if I'm going to have 3 females on my committee, since the committee has to have 5 people, that means there are going to be 2 males. So I deal with each of these groups separately. There are 6 females. I need to choose 3 of them. There are a total of 5 males, and I need to choose 2 of them so that there is a total of 5 people on the committee. So the 6 choose 3 is a value of 20. The 5 choose 2 is 10. So 20 by 10 is 200. Okay, 200 different ways of choosing that specific committee. Now, we come across the first phrase today that's new to us, and this is at least 3 females. So at least 3 females means 3 females or more. So I have 3 scenarios here. Okay, I could have where I have 3 females, right? Or that means I could have 4 females, or I could even have 5 females, couldn't I? Those are the possible scenarios, okay, where I have at least 3 females. Now, if I have 3 females, okay, the first case there, that means I would have 2 males. If I have 4 females, that means I would only have 1 male. And if I have 5 females, well, that means you're going to have no males or 0 males. Okay, I don't really have to write the 0 males in there, but I did that for the first 2 parts of this question, so I might as well write it in there so you can clearly see the calculations I'm going to do. So the 3 females, 2 males, I actually did that up above in B, didn't I? But I'll show you how this works again. So this is 6 choose 3 for the females, and 5 choose 2 for the males. Now, or, remember in math, means we add 4 females, okay, that would be 6 females, and you need to choose 4 of them, okay. The males now, 5 males, you'd only choose 1 of them, and again, or means we add, okay, or the scenario with 5 females, there is 6 females, you choose all 5 of them, okay, and then obviously with the males, you don't really have to do this calculation because it's insignificant, but there would be 5 males, and you'd be choosing none of them, okay. So what I do is figure out each of these calculations individually, and then I add them together. So we know that this gave us a value of 200, that was the calculation from B. The next one's going to be 15 times 5, so this is 75, and this gives me a value of 6. So when I add all of these together, it totals 281. Okay, so again, a couple things in that question. The phrase at least, okay, that means 3 or more. Each case is or, so that means I have to add those calculations together, okay, those 3 scenarios to give me the final solution. Okay, class example 2. Consider a standard deck of 52 cards. So last day we learned about cards, how they work with suits, okay? Red cards, black cards, face cards, okay? So again, standard deck of 52 cards, and again, we're talking about 5 card hands here, can be formed with no conditions. So no restrictions, just how many 5 card hands can you have. So there are a total of 52 cards, and you need to choose 5 of them, okay? So again, we did this calculation even last day. So 52, choose 5. That gives me a total of 2,598,960. Okay, so pretty straightforward, no restrictions. In B, okay, we have a key phrase there again, which is at least 4 red cards. So that would mean I have 4 red cards, okay? And you could say, or I could have 5 red cards. Those are the only scenarios where I have at least 4 red cards. Now, if I have 4 red cards, that means I'll have 1 black card. Okay, the 5 red cards again means you'll have 0 black cards. Again, don't really need to write that in, but a lot of people like to see it anyways. So when I deal with the red cards in the first scenario, there are 26 red cards and I would have to choose 4 of them. For the black cards in that case, there are 26 black cards, but you'd only be choosing 1. And again, or, right? Or means we would add, and then the second case here, 26 red cards, you would choose all 5 that are red. Okay, and again, this calculation won't affect the final result, but a lot of people like to write it in. 26 black cards, you would choose none of them. So as I do each of those calculations, okay, the 26 choose 4, okay, and the 26 choose 1, okay, that gives me 14,950 times 26. And to that, I would add 65,780, okay, which is the 26 choose 5. Add those two together, and you get a total of 454,480, okay? Now, C, at most 2 kings. So what does that mean to you? At most. You cannot have more than 2 kings. So what are the cases there? Well, you could have 0 kings, okay? That is possible, okay? So 0 kings, or you could have 1 king, or you could have 2 kings, right? Those are the 3 possible scenarios, okay? No more. So you could have no kings, or 1 king, or 2 kings. So what does that look like? Well, if I have 0 kings, this is what it looks like. 4 kings, I do not want any of them. So what I do is that there are 48 cards that are not kings, and I want to choose my 5 cards from those 48 that are not kings. Or, which means we add, 4 kings choose 1, and from the remaining 48 or 48 cards that are not kings, I want to choose 4 cards. Or 4 kings choose 2 of them, and from the 48 cards that are not kings, I need to choose 3 of those, okay? So there are the calculations written out as combinations. So the first one, 4 choose 0, 48 choose 5, that will give me 1,712,304. Okay, the next calculation would be 778,320. And the last one would be 103,776, okay, for a grand total of 2,594,400. Okay, so those key phrases are obviously, okay, and extremely important as I write out the different scenarios for each calculation. Okay, so again, at least, at most, okay, very different, okay, in what they mean, but the way we set up the questions is similar. Okay, now, using the complement. So this is a key phrase here, okay, complement, to solve at least or at most problems. And the first line says, sometimes using complementary outcomes can reduce the workload in at least or at most problems. So if you remember from the beginning of the lesson, that's kind of what I mentioned. The complement gives us an alternative way to solve a question in far fewer steps than writing everything out, okay? And you will see that here very clearly. So it says, consider class example 1 in which there are 462 ways in which a 5-member subcommittee can be chosen from 5 males, 6 females. Students were asked to determine how many of the 462 possible subcommittees contained at least one female. So if I want at least one female, okay, this is what the calculation would look like. Well, I could have one female, or two females, or three females, or four females, or five females, okay? So there are 1, 2, 3, 4, 5 scenarios there that I have to work out. So when I do that, remember there were 6 females, I would choose one of them, 6 females, choose 2, 6 choose 3, 6 choose 4, 6 choose 5. Those are all those different scenarios. And then what is attached to each of those is the number of ways that I would be selecting the males for each of those groups, okay? So that's what the 5 choose 4, 5 choose 3, 5 choose 2, 5 choose 1, and 5 choose 0, okay, ends up being. And this here is a typo. This should be 4 there, okay, not 5. Alicia realized there was a quicker way to solve the problem by using what we call complementary outcomes, or the complement. She partitioned the 462 subcommittees into 6 groups. Complete her work, which has been shown below. So what she's done, or what she's included in there, is 0 females, okay? Now, I know 0 females does not include at least one female, but that's really the only calculation that does not have a female in it. So we can work our way through all these calculations, but here's kind of the bottom line. As I work my way down, this is kind of what I want to focus on here. This 462 here is the total number of ways that you can select the committee. It's all of them, okay? That's all of the possibilities. What I do is I minus the one scenario, okay, or the one way to select a committee with no females, because that's the only scenario that's missing from up above. So in the end, the answer is 461, because there's only one way to select a committee with no females. So when I take all possibilities minus what I'm not looking for, I get what the question is actually asking for. And I know it sounds crazy, but that's what the complement is. Okay, so that calculation of 0 females and 5 males is the only one that doesn't have any females in it. So that would be, again, the 6 choose 0. Okay, and the 5 males, you're choosing all 5 of them, okay? So that's 1 times 1, which is just 1, okay? And that's why I have this value here of 1, okay? So that's what I select. So it says, in general, the number of ways for a required outcome is the number of ways with no restrictions minus the number of ways for the complement, or the opposite of what you're looking for. So what I did is I basically did this first one, all possibilities, and I subtracted no females, and everything else that was left was the complement, which had at least one female in the number of ways to select that group. Okay, so that is what the complement is, and we're going to take a look at how we do that in this next question. So consider a standard deck of 52 cards. How many different 5-card hands can be formed containing at least one club? Well, if I talk about at least one club, I would have 1 club, or 2 clubs, or 3 clubs, or 4 clubs, or 5 clubs. Now, that's 5 calculations that I have to basically do. But if I want the number of ways that I have at least 1 club, okay, this is what I could do instead, and this is the complement. I would figure out the number of ways with no restrictions. Okay, so that's kind of where we always start, the number of ways with no restrictions. And then I select, okay, the one scenario, or the complement, or the opposite of what I'm looking for. So I would subtract the number of ways with no clubs at all. And what I'd be left with is the number of ways with 1 or 2 or 3 or 4 or 5 clubs. So how would no restrictions look like? Well, that would be our 52 cards, choose 5. And then what would it look like if I was selecting no clubs? Well, 39 cards. Why 39? Because I remove the clubs from the deck, so that I make sure I'm not selecting one. So 39 cards that are not clubs, and I choose all 5 cards from those 39. So the calculation ends up being the 2,598,960. Okay, that's no restrictions, minus the 575,757. Okay, that's the 39 choose 5, and that gives you a total of 2,023,203. Okay, and there's a prime example of the complement. Nothing wrong with going basically the hands with 1 club plus the number of ways with 2 clubs plus 3 plus 4 plus 5. This is just a much more succinct and tight calculation, goes a lot quicker, and that is called the complement. Now, combinations which are equivalent, okay? So when we have combinations that are equivalent And again, what I'll do is I'll read through this question, but I'll circle stuff really quickly here in the write-up and just show you what exactly they're getting at. In these two scenarios, you're going to see that 10 choose 2 is going to be equivalent to 10 choose 8, okay? Why? Well, if I have 10 items and I choose 2 of them, remember, order doesn't matter or anything like that. If I have 10 things and I pick out 2, in essence, what I've also done is I've taken those 10 items and not chosen 8 of them. In either of those cases, I've created groups of 2 and 8. So if I have 10 things and I take out 2, I have a group of 2 I've selected, but I've created a group of 8 things that I have not taken. Same thing if I have 10 things and I choose 8 to remove, well, I've still created a group of 2 and 8. So 2 and 8 are going to be equivalent in terms of selecting them from a group of 10, okay? And that's what they're going to show you here with Fran and Bernie. So it says Fran and Bernie have identical collections of vintage toys. Fran selects 2 out of the 10, so your 10 choose 2 to show in a display cabinet. Since the order doesn't matter, she calculates that this is 10 choose 2, or 45 ways. Bernie selects 8 toys from the 10 to put in his cabinet, so 10 choose 8, and that also works out to be 45 ways. So explain in words why 10 choose 2 is equal to 10 choose 8, okay? Well, basically, it's what I said above. By selecting, okay, and this will take a little bit just for me to write out, but by selecting 2 toys from 10, okay, so I'm selecting 2 toys from the 10, you are also selecting 8 toys to leave in the cabinet, okay? Okay, so selecting 2 also leaves a group of 8. So therefore, the number of different selections is the same as 10 choose 2 or 10 choose 8. Okay, so when I select 2, I'm also selecting 8 to leave in the cabinet. Okay, so I'm creating groups of 10 and 2. Now, it says use factorial notation to show that 10 choose 2 is equal to 10 choose 8. So what I do is I use my formula I learned the other day for combinations. So I'll do 10 choose 2 in black. So that would be 10 factorial all over 10 minus 2 factorial 2 factorial, okay, which ends up being 10 factorial, 10 minus 2 is 8 factorial 2 factorial. Okay, the 10 choose 8 I'll do in red, so that would be 10 factorial all over 10 minus 8 factorial 8 factorial, so that would end up being 10 factorial all over 2 factorial, 8 factorial. So those are equivalent, aren't they? In both expressions, I have 10 factorial in the numerator and 8 factorial times 2 factorial in the denominator. So give 2 other examples of equivalent combinations. Well, you could have 15 choose 6, and that would be the same as 15 choose 9, right? The 9 and the 6 totals 15. So when I have 15 things and I choose 6, it's the same as having 15 things and choosing 9. Okay, and again, you know, whatever you want to do from here. So 13 choose 7 would be equivalent to 13 choose 6. Okay, the 7 and 6 again total 13, don't they? So that just takes us to this general case here. N choose R is equal to N choose N minus R. And I know that's confusing to you, and they even write it in the other way. Remember, this is the other notation we can use for combinations, but all they're doing there is they're using variables to represent the numbers like I did in C there. Okay, so nothing too crazy. Algebraically show N choose R equals N choose N minus R. I'm not going to go through that with you. Okay, you're not going to be asked to do that. Okay, that's just using the combination formula to show that. This is what I want to get to. You will see questions like this, okay, where we are dealing with problems solving for N in combinations. It says, during a Pee Wee hockey tryout, all of the players met on the ice after the last practice and shook hands with each other. There were 300 handshakes in total. Write an equation involving combinations whose solution would determine the number of players on the ice. Well, I don't know how many players on the ice, N, and how many people does it take to shake hands? Well, 2. So the number of people, choose 2 for a handshake, will equal 300 handshakes in total. So there is your equation that we're going to solve. Now it says solve by guess and test. So all you're going to do is try on your calculator, you know, like say 20 choose 2, okay, no, too low, 30 choose 2, too high, okay, you kind of go in the middle, and you'll eventually settle on that N is equal to 25, okay, when you play around with it long enough. So when you have 25, choose 2, you end up with 300. So there were 25 players on the ice. But what I'm really interested in, okay, is this. You can use guess and check, but it might take you a while, okay? Using factorials will allow me to solve this relatively quickly. So here's what happens. I start with n choose 2. Now I write that out in terms of factorials using my formula for combinations, which would be n factorial all over n minus 2 factorial 2 factorial. Okay, that's going to equal the 300 handshakes. Now what I'm going to do is I'm going to remove this 2 factorial from the denominator by multiplying both sides of the equation by 2 factorial. Now 2 factorial is the number 2, isn't it? Because 2 factorial means 2 times 1, which is just 2. So 300 times 2 is 600, okay? So again, how did I do that? I multiplied both sides of the equation by 2 factorial, which is 2, and I get 600 on the right-hand side, and the 2 factorial has been removed from the left-hand side. Now what I do is I simplify the expression on the left-hand side. So you remember we did this early on. N factorial is n times n minus 1, and I keep going, n minus 2, but I stop here, write n minus 2 factorial, because that's the same expression that I have in the denominator. And the reason I do that is because it now allows me to cancel out the expressions of n minus 2 factorial, and I am now left with n times n minus 1 equals 600. So I have a quadratic equation here, even though it doesn't look like it yet, I do. So I distribute that n into the brackets. N times n is n squared. N times minus 1 is minus n equals 600. When we solve a quadratic equation, okay, we take all the terms to one side and make the other side of the equation equal 0. So now we factor, okay? I need two numbers that multiply to negative 600 and add to negative 1, okay? And what you will see when you figure that out is it will be n minus 25 and n plus 24. I know the numbers have to differ by 1 because of this minus 1n in the middle, okay? So therefore, n will equal either 25 or negative 24. So hopefully you can see that I cannot have negative 24 because I could not have negative 24 people on the ice for handshakes. So the only solution which is valid in this question is n equaling 25. So therefore there were 25 players on the ice that created the 300 handshakes. Okay, so try that lesson today, work through it. As always, questions